Hello friends, next we are going to discuss estimation of known signal in additive white Gaussian noise channel. For this, in digital communication system, let us consider a source which producing m messages, that is m1, m2 up to m suffix m. Here each message is equiprobable with probability of 1 by m. Also, each discrete messages get converted into corresponding transmitted signal, each of duration t second. Now, during transmission through a channel, there is an introduction of noise called additive white Gaussian noise and is denoted by W function t. So we called it as a additive white Gaussian noise channel. This channel having input as SI function t and the output corresponding to the received signal, that is X function t, which is equals to SI function t plus W function t, that is for t greater or equals to 0, less than or equals to capital T. Now, as the additive white Gaussian noise is random in nature, so we called received signal xt as a sample function of received random process, that is capital X function t. Also, Wt corresponding to the sample function of additive white Gaussian noise with a mean value of 0 and variance equals to n0 by 2, that is a power spectral density. After this, the received signal xt is passed through a bank of correlators which transform it into an observation vector, that is capital X vector, which represents the sample value of random vector and equal to the summation of transmitted signal vector Si and Gaussian noise vector W. Now we note a point. Here the coordinates of vector Si are called transmitted signal point. Similarly, the coordinates of random vector X are called received signal point. Here, both coordinates are in n-dimensional Euclidean space or observation space. Now, as shown in figure, SI vector represent message signal vector and X vector represent received signal vector. And the difference between coordinates of X vector and SI vector represents a noise vector W, that is in n-dimensional observation space. Now, at the receiver side, there is a bank of n correlators, that is shown in figure. Correlator consists of multiplier and an integrator. Multiplier multiplies the received signal with basis function phi t, and after integrated we get n-dimensional sequence of observation vector capital X, and it is equals to x1, x2 up to xn, which is represented in column matrix. Here, received signal xt corresponding to the sample function of received random process, that is capital X function t, and at the output small x vector and w vector are the sample value of the capital X vector and w vector respectively, called as random vectors. Now, using observation vector sequence in the form of vector x equals to si vector plus w vector, we can determine the transmitted signal si function t corresponding to si vector. Then also we can estimate the value of message signal m cap, that is based upon the decision rule. And here the decision rule is, in order to determine the estimated value m cap corresponding to si vector, the average probability of symbol error must be minimized. And for this, let us consider estimated value m cap, which is equal to the transmitted symbol mi. So m cap equals to mi. Then the average probability of correct decision is given by the conditional probability p suffix c, which is based on some condition. Here, conditional probability denoted by p suffix c represents the probability of estimation of transmitted signal mi when observation vector X is already received, and mathematically it is written as PC equals to probability of mi sent when X vector is already received. Now, using the concept of conditional probability, average probability of symbol error is obtained and is denoted by P suffix E equals to 1 minus conditional probability. So in the place of PC we can write probability of estimation of symbol mi sent when the observation vector X already received. And according to the decision rule, average probability of symbol error must be minimized, and this is possible when conditional probability computed is maximized as there is a negative sign, and this results to the optimum decision rule, which is mathematically written as probability of correct estimation of transmitted symbol m suffix k when X vector is already received. Here X vector is the observation vector and its value must be maximum and called as optimum decision rule. So in order to estimate received symbol m cap equals to mi, the probability of estimation of transmit symbol mi must be greater or equals to the probability of estimation of m suffix k symbol, provided that observation vector X is already received. And this optimum decision rule is for all value of k equals to 1 to m, but k is not equals to I. Also, this above decision rule can also be expressed in terms of likelihood function. So, likelihood function is represented in terms of conditional PDF of received vector X given that symbol mi was transmitted, and it is equals to the continued product of conditional probability density function of its individual components, where small x vector is sample value of the random vector capital X and small xl is a sample value of random variable capital XL. Here L equals to 1 to m and I equals to 1 to capital N.